On this channel, I generally talk about new scientific discoveries that are made by scientists and astronomers all over the world that have improved our understanding of the universe. Well, today I get to do something a little bit different. I get to talk about a discovery that I made, which has slightly improved our understanding of the universe. And this discovery comes from the work that I did in my PhD. In my PhD, I used data from the Kepler Space Telescope to look for explosions that, just by pure chance, were observed by Kepler. Now, Kepler, as you may know, is an incredibly important telescope in astronomy. It was launched in 2009, and it's responsible for a complete overhaul of our understanding of extrasolar planets. That's planets that orbit stars that are not our sun. Now, through its years of its primary operation, through 2009 to 2013, Kepler observed many thousands upon thousands of stars and found thousands of extrasolar planets, changing our perspective on the universe by showing us that there are many other solar systems out there and perhaps many other planets to which life might call home. But I wasn't interested in these fantastic extrasolar planets. I was more interested in things that go boom, things that blow up in the night sky that we want to try and understand more, like supernova, or as we'll get on to, nova-type objects. So for my PhD project, I had this problem. We had all of this data from Kepler that we wanted to search for explosive events. Now here is an example of what Kepler sees, one target of the many hundreds of thousands that Kepler observed. In the center we have the star which Kepler wanted to look at and was observing for the primary science case. And around this star we have all of these pixels which are just pointing at the sky. And they're used for calibration, but not really much else. So the idea that my supervisor had was, what if we searched each one of these background pixels to try and find out if there was an explosion that happened in that pixel? So naively I said, yeah, sure, that can't be too hard, and set forth to try and understand that. And a few years later, I get to a point where I have something which works and something that can identify new transients in Kepler data. Here's an example of the code that was written to do that. Pretty ugly, I know, but it got the job done, or at least to a certain degree. And this was the first new object that I had discovered. This strange thing that bounces up very quickly and then slowly declines away before we don't see it anymore. I had no idea what this thing could be, but luckily my collaborators had some pretty good ideas. And soon we stumbled upon what this actually was. It was something called a WZ Sge type dwarf nova. Now, a dwarf nova is something like can be seen in this wonderful artist rendition of this object, done by Leah Hustak from the Space Telescope Science Institute. In the center we have a white dwarf, which is the core of a star like our sun, which has reached the end of its life and puffed off all the outer layers. Around that white dwarf is an accretion disk of material being stripped from a nearby companion. In this case, it's a brown dwarf, something that's just a little bit too small to become a star, but pretty big, so it's not really a planet. So you could say in this case that the white dwarf is acting as kind of a vampire, stealing the material, stealing the life from its companion brown dwarf to feed itself. So what did we see with Kepler? We saw this very strange and interesting light curve, which was the result of material being stripped away from the companion brown dwarf and fed onto the accretion disk. The accretion disk is pretty interesting and pretty complex. But simply speaking, what happened is that there's so much material that gets fed into the accretion disk that no particle can just kind of freely travel around in its orbit. It bumps into something else. And so you have all of these particles bumping into each other, they get very hot, very excited, and they emit an awful lot of light as they lose their angular momentum and gravitational potential and convert that into light. So this superoutburst that we saw with Kepler is the product of the disk getting too dense and needing to dump some energy. So based off the light curve, we had a good idea of what it should be. It should be this kind of WZ Sge dwarf nova. But how do we confirm that? We used an instrument on a 4-meter telescope called DECCAM to take a very precise image of the region in space where we saw this dwarf nova outburst. And if you stack different filters of images together, we end up with this color image here. And sitting right smack bang in the middle of this is the culprit of the superoutburst. This is the new object that we discovered. It looks blue in these images because the white dwarf itself and the accretion disk are both pretty warm, so emit a lot in the blue end of the spectrum and not so much near the red. So that's a good indication. We've found the exact location it is on the sky, and we also took a spectra. We measured the rainbow of light coming from this object with the Gemini telescope. And we found that this accretion disk is spinning pretty quickly. It's going about 460 kilometers per hour around the white dwarf, which is exceedingly fast from our perspective, but it's kind of run-of-the-mill for this type of object. By studying the exquisite data from the Kepler Space Telescope, we're able to see little wiggles in the light curve from the superoutburst, and these wiggles tell us that the orbital period of the system is about 83 minutes. So it only takes 83 minutes for the brown dwarf and the disk to go in a full orbit around the white dwarf. And furthermore, if we looked at the really early part of the light curve, the first few hours of the superoutburst, we found something quite interesting, something that hadn't really been observed before. We found that the brightness of the superoutburst increased very, very slowly for the first 10 hours. Then all of a sudden, it got bright extremely quickly. Now this kind of phenomena hadn't been observed before in these dwarf nova superoutbursts. So being able to discover this new indication of physics going on in a dwarf nova was pretty exciting. So this was the main discovery of my PhD. It was the proof of concept that what I had been doing was correct. And since then I've found a few more objects that we're looking into. But it is something that, without doubt, gave me my PhD. And it was found completely by chance. If Kepler wasn't looking there at that point in time, we just simply would never have seen it. And I perhaps wouldn't have had a PhD ready to go when I did. So, just by luck, Kepler is a very good telescope for studying explosions in the night.